All right, now we start doing antiderivatives. Even more fun. So first let's introduce what we're going to do by a few simple derivatives. So if you look at this first equation, a cubic equation, so we know its derivative is 3x squared. The derivative of the constant is 0. So we go to g prime of x. The derivative of the first term is 3x squared, and the derivative of negative 71 is 0. And we go to h prime of x, and the derivative is 3x squared, and the derivative of pi is 0. So we started with 3 different functions, and yet they all have the same derivative. So why would that be true? Well, because these were really functions that had the same variable terms. They only differed by a constant. So we say that functions that differ only by a constant have equal derivatives. So that's an important idea. All right, let's take a look at this graphically. If I told you that this was the graph of f prime of x, and let's say it's 2x. Well, I hope that looks familiar to you. I hope you can say, well, that's clearly the derivative of our basic parabola x squared. So if you think about that, you'd say, well, this must have been my function f. But are you so sure about that? What if function f, instead of being x squared, let me draw x squared here, instead of being x squared, what if our function had been g of x is equal to x squared plus 2? What would the derivative be? Wouldn't it still have this same derivative? So I guess I better call them all function f. So this would be our parabola, but slid up 2 units. So then I hope you've got the idea that you could say, well, why couldn't f of x be equal to x squared minus 97? And wouldn't it still have that same derivative function? So the parabola could be anywhere on our graph, any vertical translation. So notice again, what we know is that these functions differ only by a constant. So they all have the same derivative. All right, so now we're ready to start working backwards. If we are given the derivative and we want to find the original function, this would be called anti-differentiation. So when it's a polynomial here, we want to reverse the power rule. So let's think what f of x would have been. So the exponent must have been 1 unit higher, and the constant, can you think backwards? Can you reverse the power rule? Wouldn't it have to be a factor of 4? So we'd have to divide that by 4. And if in doubt, go forward again, do the power rule, and see if you get back there. So how do we reverse the power rule? We raise the exponent, and then we divide by that new exponent. So let's try it on the next term. We're going to raise the exponent to 3, and we're going to take the 6 and divide it by 3. And it only takes a second for you to check to see if it worked. And what about this term? This really would have an x to the 0 if you prefer to think of it that way. So we would have an x to the first power. So would this term have a derivative of negative 5? And now are we finished? Are we sure that's the function we started with? Or do we now realize that there could be any constant here? So when we do an antiderivative, we don't actually know the last term. It could be 0, but it could be any constant. So can we find this constant? Well, like your algebra problems, if we are given one data point, we could back substitute for x and y, and then we could solve for c. But if we don't know a data point on the graph, then we leave a generic constant c whenever we do an antiderivative. All right, let's try another example. Looks a little bit different. This time we're starting with a second derivative. So let's see if we can work our way backwards. If the second derivative of x is just 4, then wouldn't the first derivative have had to have a 4x? But then remember that it could have a constant. So I'm going to put c1 there because we're going to repeat this process. So what is that constant? Well, here we're given a data point. So substitute this data point to find c. Substitute if you are given an initial point. Substitute to find the constant c1. So what does this tell us? This tells us that f prime is equal to 2 when we put 0 in for x. So of course that's telling us that our constant must be 2. All right, so now we know our first derivative answer. Our first derivative would be 4x, and we just decided that the constant would be 2. And now we're ready to go backwards one more step. So from the first derivative, we can go back to the original function. And now we've got to reverse this. So we're saying 4x is the derivative of what term? So we raise the exponent. When it's a polynomial, we reverse the power rule. We raise the exponent, and we take that new exponent and divide 4 by 2. So we want 2x squared. And check it out. If you differentiate, you'll get back to 4x. And this term 2 must be the derivative of 2x. And then we don't know that that's the function because there could be any constant here. So can we find c2? Well, now we're going to substitute another data point. So notice we're told that f of 0 is equal to 5/2. So you'll quickly figure out here that you probably don't really have to put 0 squared here and 2 times 0. You can probably see that they're telling you that this is the value of c2. So there's our function, 2x squared plus 2x plus 5/2. So we did 2 antiderivatives. Now, go back and look at the problem because we're not quite finished with the directions. We've got one more step to go here. So just to make us read carefully, now we have to find f of 1. So putting 1 into our function, we would have 2 plus 2 plus 5/2. So 4/2, 8/2, 13/2, or 6.5 if you prefer. Does not matter. All right, let's try another. Let's keep this in mind. It's probably already familiar to you from physics. And of course, you might also remember the negative 9.8 meters per second squared if you're in meters instead of feet. So it depends on the unit. So this is the acceleration due to gravity. Of course, we're assuming that you're living on planet Earth. Different planets would have different gravity constants. So now let's make use of that to work backwards here and see what we can do now with a vertical motion problem. In your algebra classes, you were always given the formula for a vertical motion problem. Now we can actually work backwards from acceleration because think what we know. The height function, which we could call s of t, so the height or the position function for a vertical motion, we know that its derivative is the velocity function, and we know that the second derivative is the acceleration function. We've certainly seen this before. So now let's think about this vertical motion problem. What do we actually know? To start with here, we can start with the second derivative because that acceleration for a vertical motion problem is simply the acceleration due to gravity. So, whoops, I wrote 22 here instead of 32. So that's our feet per second squared. So now we can differentiate to go backwards. So the antiderivative of acceleration would take us back to velocity. So that would take us to negative 32t plus some constant. And a better name for this constant, when you put 0 in for time, notice that this is v of 0. So we would often write it as a v sub 0, our initial velocity. So when you happen to be doing acceleration, velocity, and position, instead of putting a constant c here, you might give it a better name and call it the initial velocity. And the reason that's important is because that was given in the problem. The initial velocity is the velocity which with with which the ball was thrown upward. So this is actually given in the problem to be 48 feet per second. So now we've got our velocity curve. Negative 32t plus 48. And now we can work backwards from velocity. We can do yet another antiderivative, and that'll get us to our position function, or your height function if you prefer calling it that. So we're going to raise the exponent to a 2 and divide that coefficient by the 2. And this would come from a 48t. And then we would put a constant here, but again, let's think about this constant. Is there a better name for it in this specific case? When t is 0, this term would be all that's left. So this is the initial height. This is the initial height or the initial position. So a better name for that one could be s sub 0. So were you throwing the ball from ground level, then s sub 0 would be 0 at ground level. But we weren't here. We were leaning over the edge of a cliff. So our initial height was 432. So this was given to be 432 feet. So now we know the parabola for any height at any time t. So now we could use that function to answer other questions. And we've got 2 more questions to answer. So this is our math model for the vertical motion problem. Now we want to find its maximum height. Well, for a parabola, in your pre-calc days, you would have used opposite of b over 2a as the x-coordinate of the vertex, and that would still work, but remember that we have a much better method now for question B. When does it reach its vertex? When v of t is equal to 0. That ball is going to turn around and head back down towards Earth when the velocity hits 0. And look at how simple that is. Without too much effort, you can find the x-coordinate, and of course it'll be the same as it was in pre-calculus. 48 over 32 if I divide by 16. So at 1.5 seconds, and then all we have to do to find out how high it is grab your calculator and find out s of 3/2. So at 1.5 seconds, we could give the maximum height. But in fact, our question doesn't even ask us for the maximum height. It just says when does it reach the maximum height. So that would be at 1.5 or 3/2 seconds. And I think we have one more question here. Let's switch colors again here. When does it hit the ground? So for that last question, it hits the ground would be the same as saying when is its position or its height equal to 0. When is the height equal to 0? So we could rewrite this s of t function. Let me just write underneath here. And if I factor a negative 16, if it's factorable, and maybe I'm jumping the gun there, 432 might not be divisible by 16. So I think if I don't easily see the factors, then I wouldn't spend much time trying to factor it. I would go right to quadratic formula. So we would have opposite of b plus or minus the square root of b squared minus 4 times a times c. And of course you can grab your calculator to approximate this all over 2a. And we're asking for when this hits the ground. So remember that we were at this cliff when we threw the ball in the air. So there's going to be one x-intercept in the parabola that didn't really happen in our real world problem. So we want to keep only the positive value of t. Keep only the positive t value. So grab your calculator and approximate that. And unless I've made a calculator error, I think it's about 6.908 seconds. All right, let's press on here. And I don't have my entire question visible here. You do on your assignment sheet, I hope. Okay, so here's another question where we're starting with deceleration given. So deceleration would just mean a negative value for the acceleration function. So it's just like our vertical motion problem, that we're given the acceleration, but we would start out with negative 16. And then we would work backwards from acceleration to find our velocity. So I'm doing an antiderivative, and I would add a constant. And that constant, remember, is what you would get if t is equal to 0. So instead of putting c, which is okay, but instead of putting c there, you might say, I know that's the initial velocity. But we don't actually have the initial velocity given in this problem. So I think we have to proceed and do one more antiderivative to find our position function. So we'll have two variables. So this first term, I'm going to raise the exponent to a 2 and divide by that 2. And the v sub 0 is a constant, so it must have come from a v sub 0 times t term. And then we have to add a constant and think what that constant represents when these two t values are equal to 0. A good name for that constant would be that that is the starting position. So our question here is about a car stopping. So we know that the skid marks that it leaves are 200 feet. So it takes a distance of 200 feet. And the question is, how fast was the car traveling when it applied the brakes? So we're looking for the rate at time 0. So we're looking for the rate at time 0. And what position is the car at? Well, it really doesn't matter what position. If you said that this was at position 10 feet, then this would be at 210 feet at the end. So we might as well have this be our starting point. So we might as well let this be our xy axis, or in this case our st. This would be our s axis and our t axis. So since everything is relative, we might as well put our origin right at the position where we started to apply the brakes. So it doesn't matter what constant you put here. So we might as well say, let's shift it over and have that start at our origin. So now we have our s of t function for our position. And now the problem here is that we've got to find out our other value. So now let's think what we can do to find this is our remaining problem, is our initial velocity. We want to replace that with a constant. So what do we actually know? Well, we know that when the car stops here, we know that the velocity is equal to 0 when the position of the car is 200 feet. So there's the data point, and that of course is the trouble spot here. So we know that when the velocity is equal to 0, we're going to have a position of 200 feet. So let's see what we can do with this. Our velocity, we just decided, will be 0. Our velocity will be, how do I want to write this? Let me try to organize it for you guys a little better. Let's see. V of t is equal to 0. Would be this equation. Let's see, we want to solve for this v sub 0 is what I'm getting at here. So our v sub 0 is equal to so what are we figuring out here? That time when the car comes to rest. So this is the time. This is the time when the car stops. And what else do we know about that? we know that it stops at position 200. So I think I explained that kind of oddly. Hopefully this is making a little sense, 200 feet. All right, so now let's use our position function then. So we're doing some back substituting here. I think I made this sound complicated, but our position is 200 when the car comes to rest, and we just figured out that the time when the car comes to rest can be written as the initial velocity over 16. So we've got to solve this equation and I need a v sub 0 times, oops, sorry, it's not helping at all. There's our v sub 0 and another v sub 0 over 16. So this is the time that we're putting in, and we know that the position at that time is equal to 200 feet. So t represents our stopping time. And let's see what we can do to solve that equation. This negative 8, at least the 8, can cancel with one of those 16s. So we'll just have a 2 times a 16 left there. So 200 is equal to v sub 0 squared over 32. Oh, that one has a negative sign. And our next term has v sub 0 times v sub 0. So that's also v sub 0 squared over 16. And then let's multiply that equation by 32. So we'll have 6400 is equal to negative v sub 0 squared plus 2 v sub 0 squared. And we're almost there. V sub 0 squared, take the square root. This happens to be a perfect square, so we will get 80. And our units are in feet per second, so that's our initial velocity. All right, in feet per second squared. Oh, did I just say feet per second squared? I'm not listening to myself. I think that's just feet per second. Could we change it to miles per hour? Sure, you could use your cancellation of units. So I think it will come out to be somewhere in the neighborhood of 54, actually 54.54 repeating miles per hour if you wish to convert that. All right, well, we'll have to practice that one again. See if I can make that sound a little easier for you. All right, here we're starting with the second derivative, so let's do an antiderivative. We're going to raise the exponent, divide by that 3. We're going to raise this exponent, divide by 2. This must have come from a negative 4x, and then we have to add a constant. So since this is only a first derivative, I'll put c1 so that the next time I can put c2. And which of these points can we find out what c1 is? We have no data point. We have no data point for f prime, so we'll have to proceed. Let's go back, another antiderivative. Let's go back to the original function. We'll raise the exponent and divide by 4. We'll raise this exponent and divide by 3. We'll raise this exponent to a 2 and divide by 2. Plus c1 must be in front of an x to the first power. And now we've got to add a second constant, c2. So now it looks like we're in trouble having two constants. We need to figure out whether we know these two constants. And from your Algebra 1 days, I hope you say two variables, we're in good shape because we've got two different constants. So we know when x is 0, we get a y coordinate of 4. And x is 0 is nice since it makes all of these x terms become 0. So that was a nice, easy way of telling us the value of c2. And now we only have one variable left to find. So c1 is still a problem. So now we can go get that other data point. We know that when x is 1, y is 1. So when x is 1, y is 1. And that's a pretty simple equation. So on the right hand side, it looks like we have a 4 plus c1. So c1 is negative 3. And now we know our function, x to the fourth plus x cubed minus 2x squared. And now our c1 we now know is negative 3. So that goes in front of the x. And once we know our value of our function, we don't have to do anything else here, but of course if it was an applied problem, then you could use that function to extrapolate other points or to find some missing values.